Hello everyone, and a warm welcome to the concluding module of this course. In this session, we will apply the concepts we have learned about chemical bonding, intermolecular forces, and synthetic polymers to understand the properties of materials used in the production of contact lenses. We will begin with a brief discussion on the history of contact lens development. Next, we will explore the key consumer demands for contact lenses and examine what these requirements mean for material scientists working on their development. After that, we will go through the main classes of modern materials used in lens production. We will start with polymethyl methacrylate, historically the most important polymer in this field, and then extend our discussion to its modern derivatives. We will also examine the role of polyvinyl alcohol, polyethylene glycol, and related hydrogels in the advancement of contact lenses. Finally, I will introduce you to oxygen-permeable contact lenses, focusing on polydimethylsiloxane, which is perhaps the most crucial material in the production of modern lenses. Throughout the lecture, our goal will be to develop a general understanding of the relationship between intermolecular forces and the properties of polymer materials. In 16th century, Leonardo da Vinci laid the conceptual groundwork for what would eventually become contact lenses. In his Codex of the Eye, he explored how vision might be altered by directly modifying the cornea's refractive power. Da Vinci proposed two main ideas for improving human vision. One involved submerging the eye, or even the entire head, in a bowl of water, and the other envisioned a water-filled glass hemisphere that could be placed directly over the eye. Although these concepts were not practical in his time, they remarkably anticipated the principle of placing a corrective medium in direct contact with the eye to adjust its optical properties. His work was driven more by a curiosity about the mechanics of vision than by an immediate need for vision correction. Yet it set the stage for future innovations in contact lens design. In 1637, René Descartes proposed the concept of improving vision by placing a glass tube filled with liquid directly onto the eye, specifically the cornea. His idea was that the fluid would alter the way light refracted into the eye, allowing for better focus and vision enhancement. This early thought laid some of the groundwork for modern contact lenses by recognizing that vision correction might rely on manipulating light at the eye's surface. Building on these early visionary concepts, a pivotal breakthrough occurred in 1887 when German physiologist Adolf Fick created the first truly successful contact lens. Fick's design was revolutionary. He crafted a heavy, blown glass, afocal scleral lens that measured roughly 18 to 21 millimeters in diameter and was designed to rest on the less sensitive tissue surrounding the cornea. By floating on a dextrose solution between the lens and the eye, it effectively neutralized the cornea's refractive errors. Fick initially tested his invention on rabbits, then on himself, and finally on a small group of volunteers, demonstrating that direct optical correction was not only feasible but could also markedly improve vision, albeit with some limitations in comfort and duration of wear. This milestone marked the beginning of a journey toward the advanced, chemically engineered contact lenses we rely on today. Considering the limitations of heavy, fragile glass, the development of polymethyl methacrylate in the 1930s marked a transformative moment in optical design. Polymethyl methacrylate offered unprecedented clarity, durability, and a lighter weight compared to glass, paving the way for modern plastic eyewear. Shortly after the development of polymethyl methacrylate-based plastic, Mullen and Obring developed the first all-plastic scleral contact lenses. Their design featured a central optic made of rigid plastic, which not only provided improved refractive correction, but also ensured a more comfortable fit by resting on the sclera instead of covering the entire eye surface. This evolution from glass-based designs to plastic lenses was a critical milestone, bridging early experimental ideas with the advanced, chemically engineered contact lenses we use today. Continuing the evolution of contact lens technology, a revolutionary breakthrough emerged in the 1950s with the work of Czechoslovakian chemist Otto Wichterl. Along with Drahoslav Lim, Wichterl developed a novel, water-absorbing polymer known as hydrogel. When hydrated, this material becomes soft and flexible, which allowed the lenses to conform to the eye's surface, vastly improving comfort and oxygen permeability compared to earlier rigid designs. The next significant leap in contact lens evolution came with the development of rigid gas-permeable lenses. In the 1970s, researchers sought to overcome the oxygen impermeability of early polymethyl methacrylate-based lenses, which was a major limitation. Rigid gas-permeable lenses were engineered from advanced materials, often incorporating silicone or other copolymers, that allowed oxygen to pass through while maintaining a rigid structure of the lens. This innovation not only improved corneal health and comfort, but also provided exceptional optical clarity. Building on these advances, the early 2000s marked another revolutionary step with the introduction of silicone hydrogel materials. These modern lenses combine the high oxygen permeability of silicone with the water-retaining comfort of hydrogels. This breakthrough dramatically improved corneal health, reduced hypoxia-related complications, and enabled extended wear, opening a new era of high-performance, comfortable contact lenses that continue to dominate the market today. Continuing our journey into how modern contact lenses have evolved, it's important to understand the key demands that drive their design. First, lenses must have the right mechanical properties. They need to be strong and flexible enough to last through daily use, yet soft enough to conform comfortably to the eye. Designers also carefully control lens thickness to balance clear vision with comfort. Wettability, which is how easily a lens can be wetted by tears, is crucial because it helps keep the lens smooth and prevents dryness or irritation. Equally important is oxygen permeability. The lens must allow enough oxygen to reach the cornea to maintain healthy eye tissue. Finally, water content plays a big role in keeping the lens soft and comfortable over long periods. Together, these factors ensure that contact lenses are safe, effective, and pleasant to wear. For material scientists, these demands mean a constant push for innovation in polymer chemistry. They need to develop materials that strike the perfect balance, being soft and flexible for comfort while still strong and durable for everyday use. This involved designing polymers that can be made into thin lenses with high optical clarity, yet still maintain enough wettability so that tears spread easily over the surface. At the same time, the material must allow ample oxygen to pass through and retain just the right amount of water to keep the lens moist and comfortable. In short, every new polymer must meet a complex set of requirements, making the design of modern contact lenses a true challenge and a triumph of materials engineering. The search for the perfect material has led scientists to explore several classes of polymers. For example, polymethyl methacrylate was one of the first plastics used for lenses due to its excellent clarity, even though its oxygen transmission is limited. Later, polyhydroxyethyl methacrylate was introduced to create softer, more flexible lenses that can absorb water and enhance comfort. In addition, polymers such as polyvinyl alcohol and polyethylene glycol have been used to improve how easily the lens surface is wetted by tears, which is important for preventing dryness. Finally, polydimethylsiloxane has been incorporated into lens materials for its outstanding oxygen permeability and overall comfort. In the following sections, we will examine the specific details and benefits of each of these polymer groups. While we have explored the main types of polymers used in contact lenses, it is important to note that the exact makeup of modern lenses is not always openly available. The companies that produce these lenses invest a great deal in research and development, and they protect their specific formulations through patents and trade secrets. This means that, although we can discuss the general classes of materials and their roles, the precise details of the polymers used in today's contact lenses are often kept confidential. Polymethyl methacrylate is composed of polymer chains that interact mainly through van der Waals forces and dipole-dipole attractions, thanks to the polar carbonyl groups in its structure. These interactions hold the polymer chains together, giving polymethyl methacrylate its strength and optical clarity. In polymethyl methacrylate, weak van der Waals forces dominate the intermolecular interactions, making lenses based on this polymer largely hydrophobic. Polymethyl methacrylate chains do not interact much with water or biological molecules. Water only interacts weakly with its polar ester side chains via hydrogen bonding. For contact lenses, this results in a material that offers excellent optical clarity and chemical stability, making it very durable. On the downside, the low water affinity means that polymethyl methacrylate lenses do not allow much oxygen to pass through to the cornea, and they are relatively rigid. This rigidity and low oxygen permeability can lead to discomfort during prolonged wear. Thus, while polymethyl methacrylate lenses have been historically important due to their clarity and durability, their disadvantages in comfort and oxygen transmission have driven the development of more advanced materials in modern contact lenses. Many disadvantages inherent to lenses based on polymethyl methacrylate can be overcome by using its derivative, known as polyhydroxyethyl methacrylate, in which the methoxy group in the ester subunit of polymethyl methacrylate is replaced by an ethylene glycol unit. Unlike polymethyl methacrylate, polyhydroxyethyl methacrylate contains hydroxyl groups along its chains. These hydroxyl groups create strong hydrogen bonds, not only between the chains themselves, but also with water molecules found in tears. When polyhydroxyethyl methacrylate gets in contact with tears on the eye, these interactions cause the material to absorb water and swell, forming a soft, water-rich network known as a hydrogel. Hydrogels are unique because they combine the structural network of the polymer with a large amount of water. This gives contact lenses made from polyhydroxyethyl methacrylate several advantages, such as softness and flexibility, providing greater comfort and allowing more oxygen to reach the cornea, which is essential for eye health. However, the high water content can also be a drawback, as these lenses may have lower mechanical strength, be more prone to dehydration, and sometimes accumulate deposits over time. What you saw here should remind you of the action of plasticizers, which soften rigid synthetic polymers. When we were discussing plasticizers in the previous lecture, we mainly focused on small organic molecules, such as derivatives of phthalic acid, which are lipophilic and interact with nonpolar synthetic polymers. For polymers containing hydroxyl groups or other polar functional groups capable of hydrogen bonding, we can use water or small alcohols as plasticizers. Just like synthetic polymers soften by plasticizers, hydrogels lose their unique physical properties, become brittle, and crack upon the loss of water. Another strategy to enhance the oxygen permeability of contact lenses is to introduce bulky functional groups into the polymer. For instance, a methyl methacrylate derivative possessing large and flexible trimethylsiloxy groups exhibits much better oxygen permeability than polymethyl methacrylate. This is because the bulky and flexible trimethylsiloxy groups increase free space within the material, creating pathways that facilitate oxygen diffusion. As a result, contact lenses made from these silicone-based polymers provide enhanced oxygen permeability, which helps maintain corneal health and improves comfort for extended wear. Let us now consider polyvinyl alcohol and the lenses made from it. Polyvinyl alcohol is typically produced by hydrolyzing the acetate groups in polyvinyl acetate. As we discussed while solving problems on addition polymerization, you should remember that vinyl alcohol is unstable and cannot be directly used to produce polyvinyl alcohol. Polyvinyl alcohol is a water-soluble polymer with numerous hydroxyl groups along its chain. These hydroxyl groups form strong hydrogen bonds with each other, helping to hold the polymer chains together. When polyvinyl alcohol comes into contact with water, such as tears on the eye, its hydroxyl groups form hydrogen bonds with water molecules. This interaction causes the polymer to swell and form a network known as a hydrogel. Polyvinyl alcohol-derived hydrogels are soft and highly water-retentive, making them very comfortable to wear. They offer excellent wettability, allowing tears to spread evenly over the lens surface, reducing dryness and irritation. However, their lower oxygen permeability and mechanical strength pose challenges in designing lenses for prolonged wear. One way to improve the physical properties of polyvinyl alcohol-based hydrogels is through cross-linking. In a hydrogel, individual polyvinyl alcohol chains can be connected to form a stronger, more stable network. A common approach is to form acetal bonds using a dialdehyde. In this reaction, the dialdehyde reacts with hydroxyl groups on two different polyvinyl alcohol chains, linking them together through acetal bonds, something you may recall from our discussions on organic chemistry and the chemistry of sugars. This cross-linking process enhances the mechanical strength and durability of the hydrogel while preserving its high water content. As a result, the contact lens becomes more robust and better able to withstand everyday use without losing its comfort and flexibility. Continuing our journey into polymer-based contact lenses, let's now explore polyethylene glycol and its role in lens materials. Polyethylene glycol is produced through an addition reaction involving ethylene glycol and ethylene oxide, which is also known as an epoxide. It is a hydrophilic polymer composed of repeating ether units. Polyethylene glycol chains are held together by dipole-dipole interactions, as the polarized carbon-oxygen bonds in ethers create dipole moment. Upon contact with water, the oxygen atoms in polyethylene glycol form hydrogen bonds with water molecules. This interaction causes the material to absorb water and swell, creating a soft hydrogel network. Hydrogels made from polyethylene glycol share similarities with those derived from polyvinyl alcohol in that both are highly hydrophilic and improve lens wettability. However, while polyvinyl alcohol has many hydroxyl groups that form strong hydrogen bonds, polyethylene glycol relies on its ether linkages, resulting in a slightly less extensive hydrogen bonding network. This difference can affect how the lens feels and how it interacts with biological molecules. Contact lenses prepared from polyethylene glycol offer excellent comfort because of their high water content and superior wettability. Their softness helps maintain a moist surface and reduces irritation. On the downside, these lenses might have lower mechanical strength and, depending on the formulation, could exhibit reduced oxygen permeability compared to other advanced materials. This balance of properties makes polyethylene glycol-based lenses a promising option, especially when comfort is a priority, although challenges with durability and oxygen transmission must be addressed. Let us now look at polydimethylsiloxane and its role in lens materials. As you might recall from the problems we discussed on condensation polymers and the synthesis of silly putty, polydimethylsiloxane can be prepared by a polycondensation reaction involving dihydroxydimethylsilane. Polydimethylsiloxane is a silicone-based polymer with a silicon-oxygen backbone, where each silicon atom is bonded to two methyl groups. Even though the silicon-oxygen bonds in polydimethylsiloxane are polarized, The methyl groups prevent the polymer chains from getting close enough for effective dipole-dipole interactions. Instead, the interactions between polydimethylsiloxane chains are primarily weak van der Waals forces between the methyl groups, allowing the chains to move easily relative to each other. Unlike polyethylene glycol, which forms strong hydrogen bonds with water, the steric hindrance caused by the methyl groups in polydimethylsiloxane prevents the oxygen atoms in the polymer chain from engaging in hydrogen bonding with water molecules. The presence of methyl groups makes polydimethylsiloxane lipophilic, meaning it has a greater affinity for fats than for water. One of the most important properties of polydimethylsiloxane is its high oxygen permeability. Its flexible backbone and the free space between polymer chains allow oxygen molecules to pass through very easily. This property makes polydimethylsiloxane-based contact lenses especially appealing for extended wear, as they help maintain corneal health by allowing ample oxygen to reach the eye. However, the reduced wettability of polydimethylsiloxane may cause discomfort for some wearers of contact lenses made from it. Most modern contact lenses are produced from polydimethylsiloxane and its copolymers with monomers possessing polar groups. These copolymers allow for further surface modifications to improve moisture retention. One common technique to improve the wettability of polydimethylsiloxane-based contact lenses is oxygen plasma treatment. In this process, the surface of polydimethylsiloxane is bombarded with oxygen ions, which break some of the original silicon-carbon bonds and introduce polar groups, such as hydroxyl groups, onto the surface. This modification transforms the normally lipophilic surface into one that attracts water via hydrogen bonding. As a result, water from tears can spread more evenly over the modified lens, greatly enhancing comfort and performance during wear. To sum up, in this lecture, you were introduced to the main families of polymers used in the production of contact lenses. We examined their key characteristics, focusing on intermolecular interactions between polymer chains and their interactions with water. We began our discussion with contact lenses made from polymethyl methacrylate, a lipophilic and rigid polymer with limited oxygen permeability and wettability. You saw that by modifying the ester subunits of polymethyl methacrylate through the introduction of ethylene glycol subunits, its wettability can be significantly enhanced, improving the comfort of contact lenses based on this modified polymer. We then briefly discussed polyvinyl alcohol and polyethylene glycol, as well as the physical properties of contact lenses derived from these materials. You observe that the hydroxyl groups and ether subunits in these polymers make them hydrophilic and prone to forming hydrogels. Additionally, we explored how the physical properties of polyvinyl alcohol-based hydrogels can be enhanced through cross-linking, where hydroxyl groups on different polymer chains form acetal bonds. Finally, we examined contact lenses made from polydimethylsiloxane, a lipophilic polymer with a silicon-oxygen backbone. You saw that steric hindrance in polydimethylsiloxane creates cavities between polymer chains, making it highly permeable to oxygen. We also discussed how modifying its surface through oxidation improves its hydrophilicity, which is one of the reasons why polydimethylsiloxane-based lenses are so widely used today. Thank you for taking this course and for your efforts and contributions. We wish you the best of luck in your final examination.